Thank you, Chris. Good morning. Thanks for coming that early. I'm Jakob Ringler, a TD digital artist, and I'm here to show you how to build something like the new ML Volume Upres tool completely inside of Houdini. Houdini 21 includes a tool called ML Volume Upres, but what is that? In essence, it uses a machine learning model that takes your low-res simulation and performs an upscaling operation to get more detail. You can think of it like a smart sharpening filter. Houdini ships one pre-trained model for billowy smoke, which you can access in the Pyro configure billowy smoke recipe, and a training recipe, which comes pre-configured with for the billowy smoke. But you can also plug in your own sims very easily, and today we will go through what goes into building this training recipe and how to approach similar problems. A few things that were added in Houdini 21 that make this possible are support for custom network scripts that allow for different architectures using PyTorch, custom loss functions, more optimizers, learning rate scheduling, but we will get into all of the ML stuff later. Also, there is a new TOPS ML training monitor that lets you look at your loss progression while you're working on your model. There were also a couple of other presentations that I really recommend checking out. Michiel Hagedorn, who sits over there, already presented at SIGGRAPH about general ML pipelines and the vision that SideFX has for ML future in Houdini. And Jeff Coutin and Nick Culver demoed the tool from an artist's perspective yesterday. And Jeff Coutin also presented at FMX a more technical how to work with the tool, how to automate things at SIGGRAPH. I really recommend checking those out if you're interested in a more user-focused presentation. Before we start, we need to talk about what this is supposed to be and what it is not. We are trying to build an upscaling model, as I said, like an intelligent sharpening filter that takes a low-res volume and increases the resolution by a given factor. This is not about adding entirely new shapes. The model is deterministic and not generative. It can only enhance what is already existing in the low-res in some way or form. The workflow we envision here is the following. You create some high-res simulation that you like, you train a model for that type of simulation, and then you apply the trained model to similar low-res simulations to increase the detail level. In a production context, that could be useful when you, for example, have a low-res simulation which is improved, and you just need to move a little closer, add a little bit more detail, but keep the same silhouette. Also, it could be very handy if you have to create multiple simulations of the same kind. You can think of a carpet bombing scene in a movie where you train on one explosion, then apply the same trained model to multiple other explosions that you simulate at a lower resolution. Or you want to iterate fast on a low-res sim and get a sharper result without resimming. And you can just apply the model in parallel to get the high-res. A fourth option would be you want to add detail to volumes that are too large and too costly to actually simulate in the first place. Like you can think of a field of clouds you could train on one single high-res cloud and apply the details to larger low-res clouds. We're going to create a dataset which we can use to train the model, and then we apply this model to new unseen low-res simulations to enhance them. While there's a huge amount of papers out there, we will look at a very classic one that's already 10 years old by now. The SRCNN paper uses convolutional neural networks to learn to predict high-res images from a given low-res. And since volumes are essentially images with an added dimension, it's worth giving this simple approach a try. As I said, this is fairly small and straightforward and really the most basic for super resolution tasks. And the general idea is the following. You take a low-res image, you upscale it with bicubic interpolation to your desired target resolution, and then you feed this into a convolutional neural network which tries to predict sharper results based on the input. There are much fancier things you could do, but for a first ML project, that won't fit the scope. Before diving into any implementations in Houdini, I wanted to give a very quick ML 101 for Houdini artists and TDs to hopefully make this interesting to anyone who hasn't played around with any ML yet. For Houdini people, a good way to think about a network, a neural network, is as a solver. You provide an input, the solver does some calculation, and you get something back. While the program that runs a solver is programmed manually, the function of a neural network is learned by looking at tons of examples. Networks, like solvers, have many parameters that can be changed to control the output, and the learning process is tuning those parameters in a way that improves the model's output compared to whatever target you wanted to learn. It's sort of like an artist who would tune solver parameters to achieve a desired look. That learning process is done with algorithms like gradient descent. You can imagine this like walking down a hill where you want to get to the lowest point because that point corresponds to the best performing model. There are many ways to get down a hill. And two important controls for how you get down the hill are the optimizer and the learning rate. Optimizer corresponds to who is walking down that hill. In our mountain example, hikers, trail runners, or someone on crutches would take very different paths. They may also take different step sizes, which is the learning rate. Bigger steps get you down the hill faster, but may not take the best path or find the lowest point. A couple important terms before we get into the details. Hyperparameters are those parameters that affect the model you create. You can compare those to the top-level solver settings you usually set on a simulation. And everything we do today is in the category of supervised learning. That means the dataset already contains matching that's usually called labeled input and target pairs. In Houdini, those pairs are called examples. And lastly, neural networks are not all the same. They can have different architectures and building blocks for different purposes. You can think of this as like microsolvers in a pyrosolver. Each one has a very specific purpose. One type of architecture we focus on today is called convolutional neural network. It's a type of network that is typically used in image processing applications where locality is important. That means what is close to each other. Essentially, you want the model to learn to look around a given area and make decisions based on what it sees. As the name suggests, this type of architecture works with convolution filters. And convolution filters should be familiar to some people. The way those work are you have a kernel of a fixed size, say 3 by 3, like in this case, that has some values set in it. And you move that kernel over the input image and multiply those numbers with the underlying values before averaging out the result. That allows you to sharpen, blur, edge detect, or do other things to the image. Here's an example in COPS that shows a few different commonly used convolution filters, like sharpen, blur, or dilate. In a machine learning context, those convolution filters are not set to fixed values that only do one thing, like sharpening. The model learns what values a filter should have to be useful for a given task. And you're not only learning a single filter, but multiple at once, which can detect different features like edges, certain angles, corners, or shapes. But let's get back to the SRCNN architecture. The hope is that the convolutional layers will detect different features in the input image, or in our case, the volume, and apply different filters depending on what they find there. To get started, it's best to begin with something much, much simpler. In this case, we just want to learn to predict the upscaling of a rasterized cube silhouette. Basically, double the resolution. To create the dataset, we can use the ML example subnodes, which takes care of all of the data wrangling before outputting it to a .raw file on disk for the training to use later. To implement the paper, we can use the new partitioned network script module you can find on the ML regression train node. This allows you to write out custom module architectures in plain Python or PyTorch, which makes it easy to adapt already existing solutions from papers or GitHub. Not every architecture can be expressed here, but most regression-related ones can. You only need to do this for the model. All of the other scripts you normally would have to write are handled automatically. Things like setting up a virtual environment, loading the data, setting up a training loop, exporting the model, dealing with the GPU and the CPU just happen in the background. This allows for super fast prototyping without any boilerplate code. In the script, you can set up the layers of your network and define how those connect together in the forward pass. For the SRCNN, the implemented architecture looks like this. We set up our 3 convolutional layers and the way it was described in the paper and connect them together with activation functions. It's not too important what actually goes on here for now. I just want to point out how small the actual coding part can be. Everything else can be set up super easily using the top node's parameters. You can set the optimizer, learning rate, batch size, and more. When we run the top node, we can see the training log on the work item, and when the loss goes down, it's a good sign that our model is learning something at least. When applying the model, we get the prediction in the middle. Any result in the beginning is a big win. But if we take a closer look, we can see some noisy edges showing up here, and there's multiple reasons that could be related to. But most likely is that the amount of channels in our convolutional layers isn't big enough. Essentially, we don't have enough filters to account for all the possible angles those pixels could represent. Changing the channel count on our layers increases the depth of the model by adding more filters that can be learned. There are more weights to train, and the model has a bigger capacity to learn a wider range of input and output pairings. Increasing this usually means you also need more examples to properly train the model. The results of an increased channel count can be seen here. This confirmed the suspicion, and as you can see, the prediction is a lot cleaner with more channels. Here I applied a new trained model to different inputs. This was only trained on rasterized cubes, but already performs fairly well on more varied shapes. After proving that we can get something to work in 2D at least, we can try to make the jump to 3D. Convolution can be done in 3 dimensions in a similar way as it works in 2D. Luckily for us, the layer classes in PyTorch share all the same arguments, and only the name changes from a 2 to a 3. That means we can just adapt our model by changing the class name and providing 3-dimensional inputs instead of 2-dimensional ones, and we should be good to go, right? After quickly training this on a simple noise density cube, we can check if we get an output that looks reasonable. And we do get something at least. To test if the model can learn non-linear relationships, basically if the model can look around a certain area and make decisions based on what it sees, I ran the following test. This is a beveled cube, rasterized at 2 different resolutions. One that cannot capture the bevel detail because the resolution is too coarse, and one where you can see the bevel in the voxel representation. The red one in the middle shows what you would get if you upsample a low-res one with a naive. Yeah. When we train a single convolution filter, we cannot pick up on the bevel. The filter gets applied same way across the whole geometry. The model can't understand that there should be bevel on the corners. If we train our model on the same dataset, we can see that it learned to add the bevel on the corners, leaves the flat areas untouched. This is exactly what we want. That proves that the model can learn nonlinear relationships, that it can look around and decide, oh, this is an edge, this is a flat area, and pick filters based on that. Training linear filters could be useful anyways to, for example, train deep blur or sharpening filters for cops. Now that we have our basic model up and running, we need to take a step back to look into a few caveats of our goal. The first fundamental problem is how we get our training data. We can't use actual low-res and high-res simulations, as they don't line up. Even using an up-res workflow, we can't get actual pixel-perfect overlap between low and high-res simulations. We therefore need to prepare our training data by filtering out all of the high-frequency detail from the high-res simulation and downsampling it to the expected input resolution. After a lot of back and forth, we landed in using a windowed sync filter to remove all of the high-frequency detail in the input simulation. The underlying problem of downsampling a high-res to create our training data is that the low-res still includes shapes that wouldn't naturally emerge when running the same sim at a lower resolution. Here you can see what an actual low-res sim with identical settings looks like on the right. A workflow I found pretty useful is to hand dial the low-res sim to be a bit coarser. It's not important to match any movement or high-frequency detail here, but to have similar medium-sized shapes that just vanish on actual low-res sometimes. Usually it's enough to dial up the turbulence and disturbance to get a coarser look. All of that is not important for data generation or for training, but for the new simulations we want to apply our model to. We also have to deal with a lot more data in 3D. The whole memory footprint scales to the power of 3. The way our architecture is set up means that our input model already is at 8 times the resolution, and that high resolution propagates through all the layers, leading to a high memory footprint. That means we need to build a system that chops up our volume into chunks that can be handled during training and inference on the GPU, as we can't fit the entire volume at once. For the training, we provide a number of tile pairs that include a downsampled and an actual high-res version. Those tiles are cropped from the original volume with a limited resolution. When training and applying our model without choosing the correct input size carefully, we get the following result. As you can see, there's a lot of seams in the middle. That problem is caused because the kernel we use in our convolutional layers looks at values outside of the provided chunk. There are different automatic modes that fill this area up with ones or zeros or expand the border values, but all of those will cause seams in the reconstruction because the predicted values on the border get influenced by wrong placeholder values. To really deal with it, we need to provide bigger inputs to our network that include actual correct density values in the padding region. To calculate how much overscan or padding you need to provide, you can look at all the kernel values and calculate the correct padding per layer before adding them all up. For our model, we can calculate a necessary padding of 6 per side and add it to our input. The model's Houdini exports are Onyx files. That stands for Open Neural Network Exchange. It's a file format like USD, but for neural nets. It stores the architecture and the final weight so that we can apply them. A very useful tool to look into your network structure is the Netron Model Viewer. It's a browser-based tool where you can just upload your Onyx file and it will give you this graph. This allows you to open Onyx files and see how your model is structured and how the shapes change after each layer. I marked the different input sizes at the top here. Adding overscan or padding, and therefore being able to work with bigger kernel sizes, is always a trade-off. Even like a relatively small amount of overscan and on small tiles causes the border to content ratio to be very significant in 3D. That would mean that the model has to process a lot of redundant data and during training, and even more important, during inference, which slows down the performance. Ideally, you would use a tile as big as possible while keeping overscan at a minimum to avoid redundant data processing. Your model looks like this. Okay, no more seams, but still a little fuzzy. Something that shows up in 3D even more than in 2D is the noisy edges, because the whole exploration space is so much bigger. And spillage into the empty areas that are supposed to be empty should be gone, ideally. Because of the high memory footprint, we can't just increase the channel count forever. The model also responds differently to the same shapes at different value intensities. The same swirl shape with a density of 1 will be treated differently than the same shape with a density of 10, for example. To deal with this, we need to normalize our inputs, and we don't just want to normalize everything globally, we want to do it locally. To do this, we divide our input by a blurred version of itself. This should sound familiar to a lot of people with a comp background, and is what you do for frequency separation usually. To make this work, we need to provide 2 fields to our model. One that is locally normalized and one that is just smoothly upsampled to the target resolution. We only pipe the locally normalized version into the upresing architecture and multiply the output with our smooth high-res before computing the loss. This may sound weird, but this way we force the model to learn multipliers instead of absolute values. And by multiplying on top of our input shapes, we also sidestep the issue with the spillage into the empty areas. Even if the model predicts noisy values there, they just multiply down to 0. This gives us this result, which looks much crisper. Before continuing on improving the setup, I wanted to take a step back and talk about how to train and what to look out for. The log always relates to density levels in your training data. That means different datasets can have vastly different loss magnitudes. You should therefore compare your final loss to the initial loss and see how it changed relatively, and not compare different training runs on very different datasets. To look at your loss progression, we now have a new panel, and you can find the ML training monitor on the TOPS panel list. While training it, you may want to get intermediate results and pause training or continue in another step. You can do this by running the ML train regression tab in a for loop and enabling partial training. in the training settings. This saves out a model and a checkpoint file after each loop that you can inspect. You can also use this to generate more training data on the fly as you need it and build much more sophisticated setups. And it's useful to not clog up the farm with infinitely long running jobs by splitting them up into smaller loop iterations. I may be guilty. Saving in between models lets you create something like this where I apply the different models over time, which lets you inspect how much the model actually learned during a number of epochs. One thing that becomes apparent is that the model wastes a lot of its learning capacity on reconstructing internal detail that we never see. This may be good for flame fields or anything where you can look inside, but not very helpful for dense pyro simulations where you only care about the outside. To avoid spending a lot of resources and capacity of the network on learning everything, we can mask the internals and make the model only care about the boundary region. We don't have to do that with our training data though. We can just apply the mask exclusively during training. Originally, we had this. Everything in our input goes into the model. The model does its thing, we get an output, which we can calculate the loss from. That's great, but sometimes restrictive if you only want to perform an operation during training and not inference, like we want to do now. With the unified network, we can provide different input data during training and during inference and handle the flow of the data internally. That lets us split up and move around parts of the input like we need to with the boundary example. This pre- and post-processing only happens during training, and during inference, only the orange core is applied. In practice, that looks like this. We provide all three fields during training, the normalized one, the smooth high-res, and the boundary mask. In a pre-process step, we split the data apart and only hand the two fields that will be available during inference to the core network. We keep the third boundary field on the side and multiply it with the results and the target. Similar to our multiplication change before, we trick the model into only caring about boundary values because the loss function never gets to see what is inside of the output and inside of the target. Another common process in many ML applications is data augmentation. That's the process of taking the examples you already have and extending them in different ways to get more varied examples. For the volume upres, we rotate the input tiles by 90 degrees to make the resulting model rotation invariant. We don't want it to learn specific wind directions, for example. You can do this in typical Houdini fashion by looping over each example and performing whatever operation you prefer in SOPs. Because our architecture upsamples to the desired resolution using a classic filter approach before running any ML, it is super easy to train on higher upscaling factors. You just need to change how your training data is prepared, and for ease of use, you can use a chunk size that divides evenly by 2, 3, or 4. For everything to allow for quicker iteration tests with different scaling factors. These are 3x upres results, for example. And those are 4x. Here's a render of the 3x one, where we can compare the different stages, your input, a naive solution, the ML upres, and the high-res that we trained on. The same sim with a simple split. Or to really drive home the point, a wipe. I also applied the tool to a few other types of volumes to see what works and what doesn't. This one worked really well because of the uniform shapes. There's not that much noise in the type of shapes, so the model can learn a very specific task very efficiently. Again, a static frame. You don't have to train this on density necessarily. Here's an example that makes use of the flame field done by Jeff and Nick, who presented yesterday. And this is the bar scene Jeff, Nick, and Dmitry Flazenko and I created for the launch of Houdini 21. There are lots of different fires in the scene, and they are all using the same model that was trained on a single torch simulation to upscale. If you're interested in hearing about how to deal with all those different simulations, I highly recommend Jeff's presentation from SIGGRAPH. few production tips. You should spend time dialing the available detail in the low res. Coarser usually works better. Smooth or low res will only upres to a smooth high res. There's an option on the Pyro solver called hourglass filtering. It's very useful when creating low res sims and helps avoid streaks when the resolution is too coarse. You can experiment with different specific tiles and shapes in the training data and maybe wedge what you train on to compare different models and how they perform. And one thing that Jeff and Nick discovered that was incredibly handy for Fire was to post-advect the upres result to get the nice curved flame shapes. It should be useful for any kind of transparent field, sorry. So where are we with this? The simple CNN can improve upon naive methods, and we think it can be pushed a little bit more in the future to get better results before having to rely on much more sophisticated techniques. Few tips if you plan on building anything ML related yourself in Houdini. You should start small, find the smallest viable experiment like we did with the cubes, and be very methodical and take notes and have a logbook on the side where you write down and track your experiments and what worked and what didn't. I should have done it much earlier. That would have saved me a lot of pain. Obsidian came in very handy for that. But any note-taking solution should work. Read the docs. The docs team was very active during the 21 dev cycle, and there's a lot of Houdini ML-related docs now. Lots of super useful tips directly from Michiel in there. And I hope you had a few key takeaways today. Most importantly, how to train your own model, and that you can do so in Houdini. How you could go from a paper to an implementation, and how to experiment and understand what your model is doing. I also think the general approach to dealing with volumes and how to work with tiles and without getting seams will come in handy with a lot more things than just volume upresing. I hope we see more projects that make use of this kind of hands-on machine learning in the future, now that the infrastructure makes its way into Houdini. A few links that are very handy, of course, the ML docs and the PyTorch docs. Also this Netron Onyx viewer lets you inspect your files. Archive.org is probably familiar to most people, but it has a great search engine to look for papers. And Papers with Code, which groups papers by topic, where you can look at the state of the art and then see how that evolved and came to be, and everything is presented in a very nice and approachable way. And one last thing is Notebook LM. It's a service by Google that allows you to upload PDFs or websites and just makes podcasts out of it. So you can upload a paper and you get like a 15-minute podcast that summarizes all of the most important ideas, and it comes in incredibly handy if you want to first decide if a paper is useful to even read through, so you don't have to sit down and read the 40-page math formulas. A few special thanks, of course, Michiel and Taylor for all the ML infrastructure work, Jeff Coutin, Nick, and Dmitry for the testing, tireless feedback, and the bar scene work, and Attila, who is the main Pyro guy at SideFX, for all of his feedback on which shapes look nice and which don't, and also with the recipe work. And of course, Liana Wang, who participated in our weekly group therapy meeting. And it was actually her idea to start this whole project, so you have to thank her for getting that in 21. That's it from me. Thank you, and I hope we have time to take some questions. Up there.
Hello. Hey.
Hello.
Hey. Thank you so much. That's a fantastic presentation. Have a part, maybe you have explained it, but just want to ask you further. When you were talking about generating the low-res simulation, you have a version that's downsampled. Understandably, it's generating features that you will not get from a native low-res simulation. But if you do the low-res simulation with the same setting, your bit shapes are not guaranteed to be in the same space compared to high-res. Is that a problem?
Yeah, exactly. We basically need to crop those tiles. We need an exact lineup of those two simulations, because otherwise it would just be like noise to the model, because there's nothing there, where in shape is in the high res, there's just nothing in the low res, and then there's no real relationship that you can learn from. And that's really the trickiest and hardest part, and what we are looking into, and how to efficiently, or even not efficiently, get any proper low res, high res data that matches, that we can train on. Like, getting the data is the most challenging part here.
So right now, you mean by cropping, you basically find the common areas between the low and the high and only use those areas, right?
Excuse me, by cropping?
You said right now you're doing cropping.
Yeah, we need to get those tiles to fit it into memory, right? But even like the entire simulation would have to line up to have any point you can crop from.
Yeah, gotcha. Thank you.
Thank you.
Hello, hi. Great presentation.
Thank you.
I have a question about the custom filtering that you mentioned at some point when you show like the cube, and then it was applying like a custom filter on it, and you had like a prediction. I'll elaborate the question. Can we hijack the model to basically train it on a post process that we do? For example, we apply a custom stylization on the volume, and then the model will basically predict.
Technically, yes. Like the training recipe can be extended that you can input any high-res or low-res data, and whatever is in those tiles, the model will try to learn. I think you can only push it that far, and there has to be some process that's like a slide stylization I could see working well. The more you deviate from whatever your input and your target is, the more different those become, the more challenging I can see it getting. But it's definitely worth a try, and you can just look into the training recipe and pull it apart, and as long as you provide input and target tiles, the model will try to learn what is in there.
Okay, thank you very much.
Thank you. Anyone else? No? Okay.
No more questions? All right. Thank you for the great presentation.